Thank you very much.
And now we'll welcome the second speaker, Shannon Batcher. Okay, let me first introduce Professor Shannon Batcher. He is a professor in the Department of Chemistry and Biochemistry at the University of Oregon. His research is at the intersection of material science and electrochemistry, with a focus on fundamental aspects of energy conversion and storage. He has been named as a DuPont Young Professor, a Cultural Scholar, a Sloan Fellow, and a Camille Dreyfus Teacher Scholar. He is a ISI highly cited researcher, and in 2019, he founded the Oregon Center for Electrochemistry and the nation's first graduate program in electrochemical technology. And in 2021, he was named one of the 10 finalists for the Blavatnik National Award in Chemistry. So now let's welcome Professor Shannon Batcher.
Well, thank you so much. You can hear and see okay?
Yes.
I tell. Yes, okay, wonderful.
Yeah.
So I'm excited to be here. Thank you so much for the invitation. I'm going to talk a little bit about some of our work over the last really 5 or 6 years trying to think about advanced alkaline electrolysis concepts for making hydrogen. Let's see here. So we're in Oregon. Oregon is just one state north of California in the US on the West Coast. We're in Eugene. It's at the south end of the Willamette Valley here, nestled between two beautiful mountain ranges. This is the coast, some volcanoes, Crater Lake. Eastern Oregon is dry. We have skiing. It's a nice place. This is where I'm sitting, actually, right there. That's my window behind me, right there. And our labs are at the top floor of this building. We have a lot of nice shared and independent lab space. So in our group, in general, we're interested in electrochemical phenomena. And one of the things I've done recently that I am actually quite proud of is we started a center here in Oregon focused in electrochemistry. One thing I'll point out for this audience is that I've actually made all of our coursework freely available videos and worksheets and problem sets, all via this course, this website, electrochemistry.uoregon.edu. So you can take all of our electrochemistries for free anytime you want there. There's an engineering and a sort of Bard Faulkner course. We also have the nation's only, in the US at least, program focused in electrochemistry, graduate program. If you're interested in this sort of thing, especially if you're interested in coming to the US and working, this is a good way to get into that. Okay, let's keep going here. So in our group, we work on a number of things. I'm going to talk about this work focused on both the fundamentals of catalysis, so particularly water oxidation catalysis under alkaline conditions, and how that connects to potentially new and performance and durability improved designs for making hydrogen. We also work in a related area in bipolar membranes and some semiconductor photochemistry, which I won't talk about today. Okay, so let's get to the meat of the talk here. There's basically right now 2 commercial technologies for electrolysis, at least low temperature electrolysis. There's traditional alkaline electrolysis. This is done in a highly concentrated solution, typically 30 weight % KOH at high temperature. You have, of course, a non-precious metal cathode making hydrogen, a non-precious metal anode, first row transition metals making oxygen. And it's separated, the anode and the cathode are separated by a diaphragm, and this diaphragm is porous. So it allows the permeation of electrolyte through those pores and allows the conductance, in this case of hydroxide, from the cathode to the anode. This works very well. It uses all non-precious metals, and it operates with high efficiency. The challenge is that because this porous diaphragm doesn't block the movement of O2 from the anode to the cathode or the movement of H2 from the cathode to the anode, you can't make that diaphragm all that thick or you get too much crossover. That's one of the challenges, is running these at high current densities because of the ohmic losses in this thicker diaphragm. The other challenges are associated with the need for the rest of the electrolysis plant to be able to handle hot strong alkaline solution to pump those and separate the gas from the electrolyte. In the last 50 years, there's a new sort of technology that's been developed and is now commercially available. It's called proton exchange membrane, or PEM electrolysis. And so it uses a piece of Nafion to replace the diaphragm separator. And Nafion is a strong acid. So it's a polymer with fixed sulfonic acid groups and mobile protons. So it's a selective conductor of protons. It's great because it blocks very well the crossover of O2 and H2 compared to the porous diaphragm. What that means, for example, is you can make this membrane very thin, 20 microns or so, 20 to 50 microns thick. That lowers the resistive losses across the membrane and allows you to run at much higher current densities. It also allows you to have different pressures of the output hydrogen and the output oxygen. Many times you want to compress the hydrogen, make 100 bar or so of hydrogen, but you want to output the oxygen at atmospheric pressure. You can do that across this membrane because it's able to withstand that pressure differential. If you try to do that in this alkaline traditional system, the high pressure side will push bubbles to the low pressure side. We call that a low bubble pump. But the price you pay for this is that the strongly acidic membrane does not allow transition metals to be used as catalysts. So this PEM electrolyzer uses platinum and iridium. But another advantage is because the electrolyte now is this Nafion, this solid state Nafion, you don't need to feed this system electrolyte. It actually works in pure water. So there's no soluble electrolyte in a PEM electrolyzer, where in an alkyl electrolyzer, you're pumping around strong KOH. So one of the things we're working on is something called alkaline membrane electrolysis. And there's a number of people around the world, a number of research groups attacking this problem. And the reason is as follows. We want to build a system using a membrane, a polymer membrane that conducts hydroxide. So it's like Nafion, but instead of being a strong acid, it's a strong base. And if we do that, we can feed it pure water. So we don't have to be recirculating strong KOH. And we can use those catalysts that are all first row transition metals for both oxygen and hydrogen. Okay. But this system doesn't yet work. Well, it doesn't work very well. It doesn't have performance characteristics we need to commercialize it. So we're trying to understand how these work, how they fail, and how to make them better. Particularly, we want to know the design requirements for the catalysts working at the electrodes, the membrane, the actual chemistry of the separator that conducts the hydroxides, and what we call the ionomers. The ionomers are the polymers that make up the membrane, but they're also mixed with the catalyst layer to allow for hydroxide conduction to the high surface area catalyst. I'll show you some of that in a moment. Okay, so the first thing we did in this field a few years ago to really was to establish a high performance and easily reproduced baseline electrolyzer that worked in pure water. Most of the data you see in this field, they take an electrolyzer system like this, and instead of mimicking the PEM electrolyzer and feeding it pure water, they are looking at sort of hybrid systems where you take the alkaline electrolyzer, but at the anode or cathode or both, you feed in strong alkaline electrolytes, like 1 molar potassium hydroxide. Those are interesting designs, but they don't yet meet the criteria of this pure water electrolyzer, which has some big advantages if it can actually work. Okay, so how did we do this? Well, one of my students, basically she looked at all the commercially available materials for this process. And this was a little bit of a challenge because when we first started, there were many examples of commercial materials you could buy off the shelf and put together a high performance proton exchange membrane electrolyzer pretty easily. But the materials and the baseline processes were not developed for these alkaline electrolyzers. So we started looking at iridium dioxide as a water oxidation catalyst, platinum as a cathode hydrogen evolution catalyst, not because we're going to use these ultimately, but because these are good standard materials that are easily available. And we looked at a number of alkaline ionomers and various supports for the catalyst. And we assembled this by spray coating the ionomer with the catalyst onto what's called the gas diffusion layer, and I'll show you some of that in a moment. So here's some properties of these polymers. I'll draw your attention to their chemical structures below here. These are the chemical structures of the membrane materials and ionomer materials that have the counter ions that are anions. These, note here, you don't see hydroxide here, you see Cl minus, bicarbonate. These are the forms as received from the suppliers. And then what you do is you ion exchange that counter ion, which is compensating the quatinized ammonium group, for a hydroxide. All of these have quatinized ammonium, positively charged groups. Those are essential so that you can have a mobile hydroxide. These are the structures of some of the leading polymers from these brand names for this process. So I'll skip some of the details here, but we build electrolyzers. So these are, again, with pure water, no supporting electrolyte. And we build them with the different polymers. And you can see for some of the better systems, so this Piper-Ion, this is from Nishan Yan's company, Versogen, has the best performance over these three measured. And, you know, this is not perhaps that meaningful except for the experts, but you know, the best samples that we can easily prepare are starting to be quite competitive with sort of the best performance people see, which is about an amp at about 1.9, below 1.9 volts of total applied cell potential. Now, this is still substantially worse than a proton exchange membrane electrolyzer. A proton exchange membrane electrolyzer would be down here below 1.7 volts at the same current. So there's still some work to do in improving this. But this is a good baseline to start with that doesn't have any supporting electrolyte besides the hydroxide conducting ionomer. So, but the problem with this, the primary problem, is actually in the durability. So if you look at the voltage required to drive this electrolysis current, you can see that the voltage is increasing at a constant current fast. There's two sort of degradation regimes. There's a fast initial regime where it's degrading by many millivolts per hour, and then eventually it starts to stabilize to less than a millivolt per hour in degradation rate. But the voltage here is substantially higher than the initial voltage. These other ones degrade even faster. So all these alkaline ionomers are not particularly stable. So one hypothesis we had was that these structures, particularly at the anode, might be getting oxidized, all these ring structures. And of course, there's some evidence of this in the literature. We can take the cells apart and we can do X-ray photoelectron spectroscopy and look at the films both before, this is the polymer that's conducting the hydroxides before it's being electrochemically tested. And you see clean carbon-nitrogen and carbon-carbon signatures in the carbon 1s. You see a nice nitrogen peak due to that quatinized piperidinium group here. Here it is, that quatinized piperidinium group. And you see some fluorine because there's a CF3 group in the background. After operating at the anode, if I look at the anode, I see a lot of oxidized carbon. I see my nitrogen peak is gone. That means I've lost my hydroxide conducting group, and my fluorine peak is gone as well. Okay, so what's going on here? It's clear there's chemical oxidation going on. We wanted to understand this in more detail. So what we did is we took a alkaline exchange membrane. Here's a piece of the Versogen Piper-Ion, and we coated it with our catalyst ionomer mixture. So this is sort of this region in this red box here. This is the region that's doing all the oxygen evolution in this electrolyzer stack. Okay, and so you can take this before and after running it in an electrolyzer, and you can freeze it in liquid nitrogen. And then you can cross-section it in cryogenic conditions with a focused ion beam. And we can look at that cross-section. And so here's the catalyst particle. You see there's some nanostructure of iridium oxide in this case. There's the ionomer. Remember the hydroxides, OH minus, have to come out of this membrane and go find all these surfaces of iridium oxide to make oxygen, which has to get out the backside. So this is what it looks like before. After you're done running this for 100 hours or 140 hours, what you see is just a few iridium oxide particles left. And those iridium oxide particles are no longer embedded in ionomer. They're actually just, the remainder are actually just sitting on the surface of the membrane, pressed there by a gas diffusion layer, which is typically a porous metal support. Furthermore, you see that these iridium oxide particles, some of them are actually etching into the membrane. And so this really shows you how oxidatively unstable these hydroxide conducting membranes, at least these ones that we've tested, are under these strongly oxidizing conditions. So we need to figure out how to solve this to prevent the oxidation here. And I'm going to come back to that a little bit later in the talk. Before I get there, though, I want to talk more about how we can get some detailed insight into what's going on inside these sort of complicated systems. So one of the things we've been doing, adapted from the fuel cell literature, is integrating actually reference electrodes into our electrolyzers. So this is a trick. The battery community does this. The fuel cell community does this. And what we use to do this is we use an ionic conductor strip. This is an ionic wire. It's a strip of the ionic conducting membrane. And it's attached via a tab to the membrane that is conducting current up and down during electrolysis. So we can integrate this whole system. We can put a reference electrode there, but we actually don't disturb at all the electrolysis device. So we have our two electrodes driving current, and we're just going to sense this reference electrode potential. And from the electrostatics, we think that we're essentially sensing the electrostatic potential right in the middle of the anode and cathode. So this is useful. This is what it looks like. We have better setups now. This is an early one. You can see there's the reference. There's some tissue paper that's damp, meant to keep the membrane damp so it doesn't dry out. Here's the leads driving current through the electrolyzer. Here is the so-called gas diffusion layers. And so one of the things we wanted to do was use this reference electrode to study the effects of different components of the cell on the overall performance and then the individual performance of the different components. In A, B, C, and D, there are 4 different gas diffusion layers. These are stainless steel spaghetti, stainless steel wires, micron scale, they're microporous. And this is what we take. We take this and we spray on top of it the ionomer catalyst ink to make our reactive region that you saw in that cross-sectional image. And so the structure of this support is important because the gas has to get out the bottom and the electrons have to come into it from the catalyst level. So we have different sizes here. We wanted to study that size effect. What you see in the data for the electrolyzer, the overall cell voltage, is the one that works the best actually has the smallest feature size. Maybe that's not so surprising because these feature sizes are quite large. It's going to be hard to make good electronic connection with a catalyst layer that's put on top of here with this large feature size. If you go look and separate out the anode and the cathode potential, what you can see very nicely is the cathode potential, which we didn't change the cathode when we tested these 4 gas diffusion layers. We didn't change the cathode at all. There's no change to the cathode potential. It's all within air, this very tight grouping here for all the different devices. All the change was at the anode. We can do impedance now and separate again the anode impedance from the cathode impedance for those different devices. And sure enough, you can see very nicely that all the changes are in the charge transfer component of the anode. And that's probably because of the ability to interface electrically the catalyst layer with the smaller feature sizes better than with the larger feature size. So that was a fairly obvious example that we could have predicted that the smaller feature sizes are going to affect the anode. Here's another example that we didn't behave as we predicted, but is interesting and illustrates an important point. So we use Toray paper. It's a carbon paper with typically some sort of polymer, often Teflon type binder. It's conductive carbon. It's used at the cathode. And on top of this, we coat it with some platinum carbon composite to make hydrogen, along with the ionamide. Here we did a simple study. We just changed the thickness. This is the thickness in microns of that Toray paper. And what we see is as we go from a thinner to a thicker layer of Toray paper with the same exact catalyst on top, the overall cell potential gets lower, gets better. This was surprising because the thicker ones have more distance the electrons have to move through the Toray paper, and the hydrogen gas has to move through. So why is this getting better? Well, if you look at your 3 electrode measurements, when you increase the performance of the cell with the thicker Toray paper, you see that both the anode goes to lower positive potentials and the cathode goes to lower negative potentials. So both the anode and the cathode are getting better. So how do we explain this? Well, this is actually obvious in retrospect. As we increase the thickness of the Toray paper, and if we assemble our cell with the same number and thickness of spacer gaskets, that distance is fixed. If we increase the distance of the Toray paper, we increase the internal compression on our stack, and that increased internal compression is improving both the anode and the cathode. So this shows you how complicated these systems can be and how useful having these reference electrodes are. We are now using these reference electrode measurements actually even with bipolar membranes where we have 2 reference electrodes and an anode and a cathode in an electrolyzer geometry. So they're very useful for us. Okay, so the other thing we've been doing before I get back to more durability questions is we've been trying to explore how the catalyst identity, particularly for non-precious metal catalysts, can be designed to improve performance and durability, and whether we can use these non-precious metal catalysts as advertised at the beginning, as I used to motivate the study of these alkaline exchange membrane pure water electrolyzers. So first I want to highlight a few things that we know about electrolyzers. About water oxidation catalysts. We've studied the oxygen evolution reaction in alkaline systems for about 11 years now in my group here in Oregon. And we started out, and we still are trying to understand the mechanism by which oxygen is evolved on metal oxide surfaces in strongly alkaline conditions. That would be representative of what you might see in an traditional alkaline water electrolyzer where you have liquid KOH as your electrolyte. So this would be a different application. So here's some example data from one of our early papers. This is in 2012. And this still holds. These nickel iron oxyhydroxide based catalysts, if you measure them carefully, compared to any other catalyst, they have by far the highest water oxidation activity. Now, other people have doped various other elements in here or controlled the structure a little bit, and there's a little bit of fluctuation in the per nickel or per iron performance, but largely and systematically across all the materials people have looked at, these things are the best catalysts. And what and many others have learned from studying these is that essentially any metal oxide that works well for water oxidation catalysis, they generally don't stay in liquid alkaline conditions as crystalline metal oxides. They convert to these sort of layered double hydroxide structures. And they also typically absorb iron impurities if they don't have any iron in them at the beginning, and those ions come from the electrolyte if it's not rigorously pure. Now, these materials are interesting because they're sort of molecularly porous. Notice these oxyhydroxide structures are 2-dimensional sheets, and the active catalyst phases that form or that can be made directly typically have nano-sized domains of these oxyhydroxide structures with mixed nickel and iron or nickel, cobalt, and iron. And iron is involved in the water oxidation activity. And we can see that very clearly here. If you remove all the iron from, for example, a nickel film, a nickel oxyhydroxide material, the water oxidation activity is terrible. There's a huge overpotential to start driving any sort of current at all in the absence of iron. But when you add a little bit of iron, it gets dramatically better, and you can make these sort of world record per site activity catalysts with about 25% iron in these samples. So we've studied this. There's a few things that's important to understand the context of an electrolyzer. These materials are complicated electronic materials. So the oxyhydroxides, because of this redox wave is associated with the oxidation of this case of nickel, from nickel 2+ over here to nickel 3+, or even some 4+ as you go into the water oxidation regime. That leads to a dramatic change in the electrical conductivity of the material. So of course, in an electrolyzer, your catalyst has to be electronically conductive. And the conductivity changing as a function of overpotential does complicate understanding how catalysts work. So if you go back, for example, and look at pure first-row transition metals, it turns out that iron oxide water oxidation catalysts actually have dramatically higher activity than the other first-row transition metals if you test them under conditions where the electronic conductivity is not limited. But these mixed metal systems are by far the best. Okay, so can we use some of this that we've learned for alkaline liquid electrolytes, or where we have soluble potassium hydroxide, 3-electrode cell? Can we use some of this to understand how these alkaline membrane electrolyzers, where we only have a solid alkaline ionomer electrolyte present, how they work with these types of catalysts? And we want to do these pure water electrolyzers because if we can make them work, they would sort of mimic the state-of-the-art proton exchange membrane system, but have all non-precious metals that would allow us to scale it and get quite cheap hydrogen, but they have to work at high efficiency and for a long time. So we looked again now at some metal oxide nanoparticles, and we started with metal oxides. In fact, for some simplicity, we didn't start with the oxyhydroxides. We tried them, they didn't work that well. We'll talk more about that in a moment. So we started with metal oxides. These are all commercially available metal oxides, 20 to 40 nanometers in size. There's some variability. The iridium oxide is from the fuel cell store. It has a higher surface area. This is the electrolyzer data at relatively low temperature in pure water. And you can see iridium oxide, nickel oxide, cobalt oxide, they're actually all pretty similar. Okay. And then these iron-based and nickel cobalt-based materials are a bit worse. We also measured the activity in a 3-electrode cell in 1 molar KLH. And we saw some pretty substantial differences between the different catalysts that were not exactly reflected in the alkaline membrane measurements, telling us there's something different going on between these two. So one of the things that's interesting in the variation of these catalyst performance is you can map it actually pretty easily onto the electrical conductivity of these phases of these metal oxides, even in the dry state. So these are all measured as powders. You can get the electrical conductivity or the pressed powder. And you can see that the ones that work pretty well, cobalt oxide, iridium oxide metallics, those over here somewhere, the semi-metal, nickel oxide, they all have fairly high electrical conductivities, and they are the ones that operate at low voltages. These ones operate at high voltages. So that's for the initial performance, but there's also huge differences in the durability. So cobalt oxide is actually quite, well, reasonably stable. This is a short run, only 20 hours. It still is degrading the ionomer. We'll get that in a second. And it actually starts to outperform iridium oxide after only a couple hours for water oxidation. So this is a good standard material. We've now started using this for all our electrolyzers because it gives essentially equivalent performance to iridium oxide, and it's a lot cheaper. So for research, that's a good thing. So now cobalt 304, this particular form of cobalt 304, it's a mixed valent compound, so that's probably contributes to its high conductivity. So one of the challenges we'd like to address is making cobalt 304 or doping it with other elements to increase the conductivity even more. But notice some of these nickel iron, nickel cobalt iron, these have much worse durability. Okay, so what's going on here? Why is the durability changing so much? So one of the things we noticed is we took everything apart, and after we ran these and we looked at the anode where we're changing the catalyst, we're making the oxygen. And what we find is that there's quite big differences in the XPS spectra. So the pristine sample looks like this. You see your nitrogen, your fluorine, your carbon. The cobalt 304 didn't show a dramatic change. But things like the nickel oxide, nickel cobalt oxide, even the iridium oxide showed a lot of oxidation of the ionomer. The iron oxide, the nickel iron oxide, though, and the nickel cobalt iron oxide, the ones with low conductivity, did. So there's something going on here. It looks like on the materials that are poor electronic conductors, you don't see as obvious evidence for ionomer oxidation. And this kind of makes sense because the iridium oxide is such a good electronic conductor, all this surface area is going to be able to oxidize ionomer that's in contact with. But these ones that are really poor electrical conductors, it can only do the oxidation of the ionomer and make oxygen over here next to the gas diffusion layer. So most of the film won't show oxidation. So we think that explains some of this XPS state. But there's other things going on. So one of the things we see, for example, in the XPS data for these materials is the ratios of the elements you see in XPS are changing. And this can be evidence of either dissolution or of changes in what's at the surface of the catalyst. So the nickel cobalt catalyst, after running it, the amount of cobalt at the surface that we measure actually goes down. So nickel is somehow showing up more after running. Same here is the iron nickel ratio. Nickel is showing more. But in the pure nickel iron phases, it's actually the reverse. Iron is showing more at the surface after running this. So what's going on? Well, one of the things we know about these materials, which is actually quite problematic, we think, particularly for the nickel phases that have now in our experience pretty lousy performance and durability in these electrolyzers, is they're quite dynamic structures. So here's an AFM image we took of a single nickel oxyhydroxide material that's getting driven into OER potentials. And you can see that it is dramatically restructuring. It's very dynamic. So the nickel species are moving on the surface. There's a lot of motion at the atomic scale because those nickel oxygen bonds are relatively weak. And we think that these dynamic catalysts are actually quite bad for these alkaline membrane electrolyzers because you want a coherent and stable interface between the ion conducting polymer that's delivering the hydroxides and the reactive interface that's making the oxygen. And when these things are moving around, you actually lose that tight interfacial contact. Now, in the liquid electrolyte systems, that doesn't matter because the liquid can go wherever and fill in the new nanostructure. So this isn't necessarily a bad thing in a traditional alkaline system, but it is a bad thing, we think, in some of these newer electrolyzers. Okay, so a few other things we've looked at is the role of iron items. Iron ions, so iron is, of course, really critical in traditional alkaline electrolysis for activating these catalysts for making oxygen. But what we found in these liquid alkaline systems is that iron is actually not good. And there's evidence of what might be going on from some earlier work in our group and other groups showing that the iron is also quite dynamic. You can add iron and absorb iron onto these catalysts, but the iron can also come off if it's cycled in iron-free KOH. So here's an example of a cobalt oxide electrolyzer. It's performing sort of normally. Cobalt oxide at the anode, a pure water feed, and then we add a little teeny bit of iron to the water, and you start getting this big decrease in performance. The durability goes away. But that durability is not correlated, okay? It's not correlated with oxidation of the ionomer. What we think is going on is this iron is precipitating and dynamically affecting the interfaces between the cobalt oxide and the hydroxide conducting ionomer and preventing that good ionic contact. So we think that, soluble iron, which is dissolving and redepositing, is a bad thing because of the interface, the desire to keep those interfaces coherent, much like a solid-state battery and what was discussed in the last talk. Okay, so we have a bunch of different mechanisms. I'll skip the summary here, but just say that Cobalt 304 right now is our best candidate in these nanoparticles. There's lots of room to improve it probably because it has moderate activity, it's moderately electronically conductive, and it's the most structurally stable during a water oxidation reaction. So we think this is why this particular form of catalyst worked quite well, and we could improve it. We can improve each of these with rational control, which is something that I think is an opportunity for the field. Okay, so now I want to go back to this durability question. In my last couple minutes, I'll try to leave just a couple for questions. How do we solve this durability challenge? So one idea is to go away from the ionomers that have conjugated ring systems and go to ionomers that have no conjugated rings. This is something that this guy, Paul Cole, professor at Georgia Tech, well-known polymer scientist, he basically told this to me, 2 years ago. He said, if you use all sp3 carbon, you should be more oxidatively stable. And so he's been developing those ionomers here. And here's some results actually from his work with Wilma Stain, showing that they can get reasonable stability, a bit better than us, but the voltage is still pretty high compared to a pure KOH system, so this is not doing its job. And there is some worry about the stability of these cations in strong hydroxide. We started working with a collaborator who's developing these inorganic cations. We can put these selectively at the anode, and it seems to be improving the stability. We're seeing a decrease in voltage. There's a lot of reasons that could be. We need to understand it's very early data, but that's one strategy. A final strategy is to think about much of the way we actually heard in the solid-state battery community in the last talk thinks about controlling interface design. So one of the ideas we have is we're trying to actually passivate the interface of the catalyst, and the electrolyte, in this case it's a solid ionomer electrolyte, allows some hydroxide conductivity but prevent the direct oxidation. So we've been coating with things like hafnium dioxide. It's interesting, if you put a little hafnium dioxide on bare iridium, it actually gets better for water oxidation catalysis. We don't know why that is. If you do that, you can actually protect it from oxidation to a significant extent. So here's some XPS data showing how when you don't have a protective layer, you lose a lot of your functional groups at the anode, but with a protective layer, you don't. We haven't fully got this working at a sort of commercial level of success, but it's looking promising. And here's just some electrolyzer data, again, showing improved durability, improved performance with these interfacial layers. So there's a lot to do here, controlling the interface, just like in the battery community. And I think the future is bright for these alkaline systems if we think about all the various durability and activity mechanisms and control that. So thank you, and I'll end right there.
Okay, thank you very much, Professor Batcher, for this very enlightening talk. So now is the question and answering time. So may I invite a question from the audience? Is there any questions? Okay. Let me ask a question, a short question. So, in one of your nickel-based catalysts, you show the very dynamic change, right? So, what is the driving force for the movement of those nickel ions?
Yeah, so in this case, we've a little bit forced the system into a state where we expect to see a lot of dynamic change, because this is a monolayer, a single layer of nickel hydroxide, that layered structure that we've exfoliated from a crystal, a stacked crystal of this, following some methods by a Japanese group, can exfoliate these and put them on the electrode. So this structure, if the dynamics allow, if the bonds are sufficiently weak so that the nickels can move, we'll want to lower its surface energy by making more three-dimensional stacked geometry. So I think this is mainly driven by a surface area lowering phenomena, but we have other materials, nickel cobalt phases and things like that, that are actually more dynamically stable. We've done the same experiment actually with a pure cobalt oxide nanosheet, and you don't see this dramatic restructuring, which is sort of consistent with the stronger cobalt oxygen bond relative to a nickel oxygen bond, slowing the kinetics for the restructuring process.
Okay, thank you very much. So any question from the audience? If no question, let's thank the two speakers for this first session once again. So thank you very much, and we will end this first session in the morning. The next session will be started in 10 minutes. Okay, so we just have a 10-minute break from here. So thank you. Thank you.
Thank you all.